if we were to take a look at another object that has cylindricity, or this characteristic of having an axis that it spins about, the cone is cylindricity, right? Big circle on the bottom, and then looking down on it from the top, we really wouldn't see the tip. The tip is simply a point there at the very center. But how about in the side view? What will we see in the side view? See, we would see a triangle that has a base the same size as the diameter of the circle. It's a triangle. If you trace over the profile with your eye, the shape is simple to see. And then because, again, it has the characteristic of being cylindrical, it has an axis that we could revolve it about. We're going to take the arrow, we're going to use the bow, and we have to shoot the arrow into this view here to indicate that this is also cylindrical. Is there a need for a top view on a drawing like this? Well, let's see. Front view is a circle, side view is a triangle. What's the top view going to be? Same exact triangle, isn't it? Yeah, no matter where we turn the cone, it's always the same exact triangle. So no need to make the top view unless there was a hole drilled through this or there's some part bumping out of it. But on a simple shape like that, two views would be more than sufficient. One of the common things that I see that is a mistake when drawing cylindrical objects is that people want to get artistic. And by artistic, here's what I mean. Here's looking down on a cylindrical object, and then what happens is maybe we'll project down those two quadrants to get the height. And then what I've seen people do this. And do you see what I did there? Do you see how I added a little bit of a curve to the top and a little curve to the bottom? A little arc. So now, why on earth would somebody do that? Well, one of the reasons is because if this was a cylindrical object and it was big, let's say it's a water tank, okay, we're going down to Truxton Ave and we see a big water tank. And we know the water tank is cylindrical. It is round at the top. And then we look at it, and you know what you're going to see? You're going to see this. You are going to see curvature. And you might see it up on the top. You might see it down on the bottom. It just depends on where you're standing. This is how our eye sees things. And this is called perspective. Okay? This is called perspective. You will notice the curvature as the object comes closer to you. And that's not a bad thing. It doesn't mean that your eyes are broken or that you're seeing things incorrectly. It's just in engineering graphics, when we draw things, we're not drawing things in perspective. We're drawing them as if they were completely flat, right? It's like I'm holding this thing 3 inches away from my eyeball, and I'm looking dead at it, and my eye is just tracing the outside edges that I can see, right? And if you do that, there's no curve going up. There's no curve going down. So I wanted to point that out. Some of my more artistic students might want to do a little bit of this. No need. And of course, we already discussed that. The way you can tell that this object is a cylinder is not by doing the art class trick of shading. We don't have to create a gradient shade on the edges here. Right, how do we know it's cylindrical? We know it's cylindrical by looking at the other view, the top view. So no shading, please, not necessary. And no tricks of perspective, trying to get this to look some way that it would not look in engineering graphics, which is completely different from the way things look when we look at them with our eye and we look at them in perspective. Another application for drawing cylindrical shapes would not be for solid cylinders, but for cylinders that have been removed for an object, and what I'm talking about is a hole. So we can imagine this is a block of metal, and there's a hole that I've drilled through it, and in order to draw this in engineering graphics format, what I need to do is I need to draw the edges of the block, and we need to draw the hole, and then of course we need to indicate where the center point of the hole is, so that not only is the hole drawn or fabricated the right size, but it's also put in the right location. So I've got my sketch here of my front view, and I've got my block, and I've got my hole, and I've got my center mark. So now the question becomes, what's going to happen over here and up here? Do you know, looking at just this view, that there is a hole going through this object? And of course the answer is no, we can't tell that. But if we could see through objects, you would. You would see it. So how do we solve for this? Well, we're going to do this. We're going to go to the top of the circle at the top quadrant here, and then lightly project across. And then where we hit the object and it turns into the object, we're going to add some hidden lines. And this is representing the top of the tunnel created by the hole. We're going to do the same thing down here at the bottom. We're going to lightly project over, and we're going to add some hidden lines to where the bottom of the tunnel would be. So if we were working with civil engineering, this would be the soffit of a pipe, maybe, the inside hollow spot, and this would be the invert, the lowest point of the tunnel. Soffit, invert, the highest point, the lowest point. So that's what we're showing here in this side view. And now somebody picking this up who speaks the language of technical drawing is going to know exactly what's going on here. That this is a hole, and it goes all the way through the object. Now there's one more step left, and it's related to the bow and the arrow, right? Because if we have a center mark in this view on the circle, it means over here we're going to need a center line to indicate the axis of that tunnel created by the hole. Okay, let's do the same thing up in the top view here. I need to indicate that there is a tunnel going all the way through that part. I will bring over the quadrant point over here, and I'll bring up the quadrant point right over here. And where those two projections hit the object line, we'll add a hidden line and a hidden line. So now what are we indicating? Is this the top and bottom of the tunnel? Not really. If this is the top of the front view, then what we're looking at is we're looking at the right side of the tunnel. And over here, well, this is the left side of the tunnel. So what the hidden lines are showing here is the extreme right extremity of the tunnel and the far left extremity of that tunnel. Do we need anything else? Well, you know it. If we have a bow and we have an arrow loaded, we're going to have to shoot it into the next view. So we would need a center line in the top view to indicate that that hole is cylindrical. Okay, now this is a very freaky thing. I understand if this is a little confusing because circles don't have corners. Why are we drawing lines if circles don't have corners? Well, in this case, the line, the hidden line, doesn't indicate a corner. It indicates the farthest extent of the opening inside the solid piece of material that's been cut out. Top of the tunnel, bottom of the tunnel, far left side of the tunnel, far right side of the tunnel, created by those holes. In the example here, this might look like we're basically doing the same thing that we just did. If I have a round hole, I have to make hidden lines in the top and the side to indicate where the hole is. Would my drawing here look exactly the same? What do you think? Well, let's think about it. Corners get projected, right? So those corners get projected over and up and over and up and up and over, and we see that there is a need for some hidden lines here and some hidden lines here. So now this is starting to look a lot like the one we just did, which might be confusing or a little worrisome because the last one we did had a round hole, and this isn't a round hole, this is more like a square cutout or a square brooch. So the question is, are the two drawings in the top and the side going to be exactly the same? Does a round hole create anything different in the other views that we're not seeing here? So if you have a sharp eye, you probably notice that there's a center line here and there's a center line here. Why is there a center line? There's a center line because there's a center mark, and there's a center mark because this is round, which means that this is cylindrical and it has an axis through its center. How about a little square brooch here? Is that round? Well, obviously not. Will I add a center line over here and over here? The answer is no. There's no cylindrical property, there's no need for a center line, and there's certainly no center mark right here on this inside square. Now, before we pick up our tools and start trying to create some of these multi-view drawings with the tools, there's one last thing I want to show you. It's kind of important, and it's going to prevent you from making mistakes if you follow this technique. So in my sketch here, let's take a look at the shape I'm making. I've got this little L-shaped block, and I projected some lines up from the corners. And I have my top view. And now I'm going to make the side view, and I want you to pay particular attention and try to figure out what's wrong. What have I done wrong? So if you have an eye for detail, something that might stand out is that the height of the front here matches the height of the side. And the width of the front matches the width of the top. And of course, that's easy to do when you are projecting the corners up and over from your first view into your other views. But there's something that is not lined up. Okay, and you probably see it. It's the depth. Right, because that's the depth in the top view. Here is the front edge, here is the back edge, and it looks pretty deep, right? And now look over here in the side. This is the front edge. This is the back edge. This is nowhere near as deep, is it? So look, I get it that it's just a sketch, and it's not that big a deal because we're not measuring stuff, but this will be a problem later on. It will be easy to make mistakes making multi-view drawings unless we have some kind of system in place to prevent accidentally making things the wrong size when things should match up. And again, it's always the depth that's the problem, because width is projected up, height is projected over. This is the biggest chance for screwing up, and I want to show you how to avoid doing that. Alright, so what I have here is I have a drawn out with tools version of what we were just looking at on the sketch. Here is my front view, and of course in order to create the top view I need to lightly project some lines up from these corners so that my widths in the top match my width on the front. And after I think about the spacing I'd like to incorporate here, I'm going to set this up for its depth. Okay, and then I've drawn things very dark. My projection lines I've made very dark so you can see them easily on the camera, because if you can't see what I'm doing, there's really no point in you watching a video. So just understand that those projection lines would have to be super light normally, but I'm making them extra dark so that you can see what's been done. Okay. So now, how do I get the side view to match what has already been done in the front and what's already been done in the top? Well, that shouldn't be too hard, right? Because I'm going to project the corner to the right, and I'm going to project this corner to the right, and I'm going to project this corner to the right. And that makes sure that my heights in the side match my heights in the front. The thing that we can have potential for disaster is depth. And we don't want to make the depth here different than the depth here. So let me show you how to not make that mistake, and it works every single time if you just do it. What you want is your 45-degree triangle. Okay, this does not work with the 30, 60, 90 triangle. Okay, so you have to have the 45, 45, 90 triangle. Okay, make sure it looks like an isosceles triangle or a right triangle with a 45 degree before you try doing this. If it's this goofy looking scalene triangle, you're going to get bad results. Okay, so what are we going to do? Are we going to take this distance here and make sure we wind up with the same distance there? Quite simple. I'm going to find this spot out here in space. It's the intersection of the far right edge of the front view and the far top edge of the front view. Right? It's where these two lines crossed each other from projection. And then what I'm going to do is I'm going to draw a 45-degree line right there at that point. Okay, so what next? How does this line, the 45, help us to take this measurement and get that same measurement over here? Well, what I can do now is I can go back up to my top view and I can start projecting the corners over to that line. See, I can project that corner to the right, and I will project this corner to the right until it hits that 45-degree line. And then what you can do is you will bend the line. You'll find this point here where the projected line hits the 45, and you'll come down. And you do the same thing here where the projected corner from the top hits the 45 line. Find that point and then come down. Okay, and what you just did is you took this dimension here and you telegraphed it around the corner and down into this view. So I didn't have to measure anything, right? And that's the problem with measuring. Every time we measure, there's a chance we might make an error. If we make an error at some point, we got to go back and fix it. So showing you how to do this will prevent errors from happening that could be avoided. Okay, so let me do a little bit of cleanup here. What we should see and understand is the side view was made by projection. There was no measurement involved there, was there? I projected this corner, and this corner to create the heights. I projected this corner and this corner over to that miter line and came down with them to project the depth. This 45-degree angle, just look around your house. Look at the door frames. If the door frame is 2 inches along the top and then it wraps around a 90-degree corner at a 45-degree cut, how wide is the door frame here? It's the same, isn't it? Look at picture frames. If it's a 1-inch wide picture frame here and it wraps around a 45-degree cut in a 90-degree corner, how wide is the picture frame on the side? It's still 1 inch, right? It matches whatever this measurement was. So this is called a miter line. Miter line's got to be at 45 degrees. You can put it anywhere you want, but really this is probably the best place for it, even with the top of the front view and the far right of the front view. Because if you put it here, not only did I get the sizes right for the depth, I also got the gap. Well, it's exactly the same gap here. Right, so that's one less thing to measure too. Now, this drawing is not beautiful, okay, but the point was I wanted to show you how that miter line worked. So as we start working with the tools, you'll understand that you want to take your depths and wrap them around into the side view. Or if I give you the side view, you can work it backwards. You can work and project up to the line and then over into the top view. You see, it'll work either way or both ways. So this is one way to create your side or top view from two given views using a miter line. There's a couple of other ways to do it. One of them involves using a compass. We could do something similar by finding that point and then swinging some arcs with our compass to go from one view into the next. And there's no wrong way to do it, right? As long as this dimension and this dimension match, and this is the easiest way with the miter line to go about figuring that out.